All right, so let's see how we can apply all these things that we learned in the previous couple of classes in R. And after watching this video, I think you are going to feel a lot more confidence and relieved that, okay, do I need to memorize all those calculations? The answer is no. You only need to know how to apply them in programming languages like R or Python. So in this course, we're going to cover the R version, and you can Google things for yourself to learn how to do it in Python as well. All right, so let's quickly load these couple of libraries. I already loaded, so let's load them again. There's library Wooldridge and dplyr, clear the console, and then move on. We're going to work with one of the data sets called CEO salary. So if you are curious to explore what is CEO sal 1, it's a Wooldridge data source, and it is actually reporting the salaries for CEOs. So it has 209 observations with 12 variables. And these are 1990 salaries, by the way. And so, for instance, you see that there are a bunch of variables. One is salary, the other one is percentage change salary, sales, and etc. The goal is to, if you can relate the CEO salaries with their return on equity. Okay, these are something that we're going to cover extensively in the course. We want to see if there's any causal relationship between ROE, return on equity, of a man in a company with its CEO salary. These are really interesting questions in the corporate finance world. Okay, we can look at the head of the data set. So, again, for instance, this is CEO number 1, and these are in $1,000. So we're talking about $1 million here. So the salary number, the CEO number 1, the salary is $1 million, and etc. Right? And the return on equity for this company was 14%. So maybe the higher the equity, the higher the salary. But these are the questions that we're going to answer with econometric. But that's not the case. So let's quickly use some descriptive statistics, the functions mean, standard deviation, median, and etc. And we will get back to these interesting questions down the road when we learn the theory of econometrics. Okay, so the first one, average. So simply we say mean, open close band, and then you pass the variable, which is a vector of salary. And then this is a new thing. When I do comma na.rm is equal to true, basically I'm telling R that get rid of the NAs for me. NA remove. So we write it NA dots remove. So NA remove and then equals to true. If you start typing NA, it will automatically suggest you. So NA, see, when I do NA dots, then it suggests that are you looking for NA remove? I say okay. And I do true. When you write true, it was going to suggest you, it should be all capital letters. So when I do that, automatically behind the scene, it's going to get rid of the NA variables and then calculate the average for me. Because remember, if you include the NAs, it's going to make your average or median or whatever biased. So we don't want to work with biased numbers. So the mean salary is $1,281,000. The median is 1 million. Is it? Are you surprised? No, because remember, the salary is going to be right skewed. So if it is right skewed, the mean is going to be greater than median, greater than mode. So which one should I rely as a measure of central tendency? The answer is this, median. You can look at the standard deviation. Standard deviation is 1,000,372. So this is the standard deviation. We can look at the summary. The summary is going to show all of them to you in one line of code. So I have median, I have mean, I have the first quantile, I have third quantile, quartile, I have minimum and maximum. So in this data set, remember guys, this is 1990 data set. The minimum salary for a CEO, which was $200,000, almost $200,000, which is crazy, right? But these are most probably the top Fortune companies, and today the numbers are even a lot higher. Okay, we can also look at the correlation. So for instance, what is the correlation between salary and ROE? So before running this one, what do you expect to see? A positive number or negative number? At least, again, we know there's no theory for that. What do you think? I just want to, there's no right or wrong answer. Just what do you think? And then we will see if the data support your thinking or not. Do you expect to see a positive relationship between ROE and salary or negative? So maybe the answer is positive. So let's run the correlation. Yeah, correlation is positive. It's not small, it's not huge either. It's about 11%. Okay. And the goal in this course is to make sure that this is not pure correlation. So we have to control for some other explanatory variables, and then we can interpret this correlation. All right. Now let's move on and look at a bunch of these distributions. So these ones. So we are going to cover the discrete, one of the discrete ones just for fun, even though we're not going to use it in the course, but I just want to show you how we can calculate those things that we did in this. If you remember, we did this thing manually. I want to replicate this thing for you. I want to replicate this table, you know, the PDF, CDF. This one. I want to replicate these numbers for you. In R. Okay. So imagine our example was, the random variable was number of, well, in the whiteboard it was number of heads, but now here let's call it number of tails because I want to go from 0 to 2, not to 1 to 0. So let's say it's a number of tails when flipping a coin twice. Okay. And so remember, this is from the whiteboard that we have. These were the outcomes: head, 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 tail, tail, head, tail, tail, and 0, 1, 2. The PDFs were 1/4, 2/4, 1/4. The CDFs were 1/4, 3/4, and 1. So what is the distribution when you're flipping a coin multiple times? From your stat background, it's going to be binomial, right? So I know that the distribution is binomial. And let's say, what is the probability that if I flip a coin and I see one tail, right? I want to calculate that one. So one tail, you can look at this and say, okay, probability is 2 out of 4. The answer is 0.5, right? Let's see how we can do it in R. So what are you looking for? PDF, probability. So what is the acronym? D. What is the distribution? Binomial. So we use D binom and look at the features in the table. Oops, sorry. D binom, where am I? D binom here. What do I need to pass? I need to pass the number of, X, number of, for instance, in this example, tails, N, number of trials, we are flipping a coin twice, and P, probability of success, which is half. If you're flipping a coin, probability of seeing head or tail is 50%, right? So let's pass those numbers to the R function. Remember, if I want to see one tail, so it's 1, 2.5. So go back to R, 1, 2.5. So if I run this line, the answer is going to be 0.5, right? If I want to see what is the probability to seeing no tail, the answer is 0.25, right? Because it was 1/4. If I want to see two tails, the answer was again, the probability was, if I change this one to D, the probability was 1/4. But if I want to look at the cumulative distribution function, I use the acronym P, and you know that the CDF for, if you want to see two tails, and less, so it means two tails, one tail, and zero tail. So it's cumulative, and the answer is going to be 1. Okay. All right. Then, this is just a fun exercise for you to show you, the R is a lot more powerful than these basic things. You can pass a complete vector of, binomial random variables, right? So imagine I want to pass 100 number of draws. I want to flip a coin 100 times. And I want to see the PDF and CDF for all those 100 times, right? If I do something like this, N is 100, my random variable is a sequence between 0 and N. So if I look at the random variable, it's going to be between 0 and 100, right? And then let me actually start with 2 that you're more familiar. So if I look at my random variable, this is flipping a coin twice: 0 tail, 2 tail, and 1 tail, and 2 tails, right? Now I can pass the whole vector of dbinom of this random variable to dbinom function and save it as PDF and CDF. So we show the PDF with a small letter f and then CDF capital letter F. Now let's look at f of x. See, this is the table that we replicated: 0.25, 0.5, 0.25. What is this CDF, f of x? 0.25, 0.75, and 1. Now I can do repeat this. Remember, this is experiment. Define the definition of experiment. Now, you should be able to run these experiments for unlimited number of times, and the set of outcomes is completely well defined. So let's do it 100 times. If I do it 100 times, I can look at f and x. So f of x is going to be this, right? So then if you plot this one, you're going to see that it's going to be close to bell shape or something like that. Not bell shape. These are discrete random variables, right? All right, so again, if you want to plot this, we should see something like this, going back to whiteboard. So the plot for the, look at the black one. The plot for when r is equal to 2, we see something like this. But we can, if I increase this number, I'll see lots of these things. Right? We're going to eventually see something like this if the number of trials is 100, not only twice or 2. So let's actually have fun and look at that. So let's look at the plot of f of x. See? It's going, so basically these are the ones that we were trying to plot in the previous class and on the whiteboard. And I can also plot the f of x as well. This is the CDF, right? Remember, it approaches to 1. Here, this is discrete. It's going to be exactly equal to 1 at the end of the day. And then it starts from 0, right? So this is a CDF, PDF, and etc. All right. Then lastly, let's talk about calculating the areas under the curve. So this is the one that you're going to spend a little time. So going back to the whiteboard, let me actually try to see if I can draw something here for you. So some basic question from the statistics. Pause the video and try to come up with the answer without, before me going over the answers. So imagine I want to calculate something like this. This is a normal distribution. Here is 0. What is the area under the curve to the left? Without doing any calculation, you know that this is 50%, right? 0.5. How do we do it in R? So what are you looking for? You're looking for the PDF area under the curve from 0 to the left. So basically, this is the CDF of 0. So how do I show CDF of 0 in R? So what are we looking for? CDF, what is the acronym? P, what is the distribution? Norm. For normal distribution, and if it is a standard normal distribution, so with the average 0 and the standard deviation of 1, you only need to pass one number. So how do I know that I only need to pass one number? Let's go back to slide. So standard normal distribution. So we only need to pass one number because mu is going to be equal to 0 and sigma is going to be equal to 1. So I don't need to specifically pass them. I can, but I don't need to. So if I do p norm 0 in R, what is the answer? 0.5. So let's look at that. Okay, so p norm 0, what's the answer? 0.5. So let me clear the console for you. So p norm 0, the answer is 0.5. What about p norm 1? So what are we trying to capture here? Let's draw it. So let's draw another standard normal distribution. So here is 0, and then here is 1. So p norm 1 is going to show me this area. The area under the curve to the left of this number that you're interested, right? So what do you expect to see? A number greater than 0.5, right? So let's look at that one. P norm 1, it's going to be 0.84. And what about P norm, let's say 1 million? So if I go to 1 million here, let's say this is 1 million. Is it 1 million? Yep. What is the answer without doing any calculation? What is the area under the curve on the PDF at the end of the day? 1, right? So this is the CDF of the infinity, right? So 1. So let's see if we get some number close to 1. Well, we get actually, this is very close to 1. It's not exactly 1, but we'll see it's rounded up to 1 because it has many, many decimals, 9999999. All right, so this is how we can calculate the CDF for continuous random variable. And then for your homework 3, you're expected to do something more complicated. Let me actually solve this one for you. Actually, I have to make it 2. What's the probability that absolute value of x is less than 2? So let me quickly solve this one for you, and we should conclude the session. All right, so let's say the question of interest is, by the way, I believe this is, you see something very similar in your homework. So we want to see what is the probability, PR, P, it really doesn't matter. No, if I write PR or P, so that your random variable absolute value is less than or equal to 2. So we know that, so how can I open up this one? This is equivalent to x is less than equal to 2, or x is greater than or equal to -2, right? So basically, if you're interested in this thing, so I have 2 here, I have -2 here, and let's say x is, your homework is going to be a little more challenging. I solved it for a standard normal distribution, but the homework is not a standard, so these numbers are different. So this is 5 or something like, and there's a standard deviation. You should be careful about that one. But let me solve this version. So you want to calculate this area. There are many different approaches that you can find this area, but let's explore a couple of them, and then you can have fun and try to come up with a bunch of other ways. So I can do it, oh my goodness, sorry guys. I can do it this way. So first I can say, calculate this area for me. And because I know it's symmetric, this area is going to be the same. So I do 1 minus 2 of these guys. So if I do 1 minus 2 of these guys, that's the answer, right? So how can I calculate the green one here? Normal is symmetric, right? So it's going to be the CDF. This is the easiest one, CDF of -2. So this is the CDF of -2. And because it is symmetric, this is going to be also equal to CDF of -2. And CDF of -2 itself is equal to 1, oh my goodness, 1 minus CDF of 2. All right. So what is 1 minus CDF of 2? Let me quickly show it to you. This is the CDF of 2. So 1 minus CDF of 2, CDF of 2 is 1. So these are all the same, right? So if I say CDF of -2 or 1 minus CDF of 2 will give you the same answer, right? And then, so if I finally do 1 minus that number, you get the answer, right? So this is one way. And let's see, what do we have here in our R? So yeah, I did it differently here. So let's do it. So this is one. We're gonna do it. So let's call it the green one. Let's call this green shaded area A. And so I have another A here. So we have 2 of these A. So the answer of that blue shaded area is going to be 1 minus 2A. Does that make sense? So this is one way. We're going to explore this in R later on. So let me show you. This is the blue shaded area, or the answer to this one. So it is one way. Let's explore another way in another color. So let's use red. Let me actually plot this same thing again. 2 minus 2, we're interested in this blue shaded area. I can do it this way. I can say, you know what? First, give me the CDF of 2. What is the CDF of 2? Everything, right? So I'm really close to answer, but I don't like this part. I have to get rid of this part. So what is this part? CDF of -2. So if I do CDF of 2 minus CDF of -2, does everyone see that? So if I do CDF of 2 minus, sorry guys, the reason that it's jumping up and down because it's not in the writing version mode. So -2, it will be the answer for the same question. So pause the video and make sure that you understand this thing. So it's, again, and this is something that you're going to do a lot when we get to hypothesis testing and joint hypothesis testing and things like that. And you will become very familiar. You know, historically, students, initially they find it difficult, but at the end of the day, you can do it in 2 seconds. It's really fast when you do it in R. Okay, so let's see if we get the same answer in R. So first we're going to do it this way, and then we're going to do it this way. CDF of 2 minus CDF of minus 2. So what is CDF of 2? P norm 2. What is CDF of minus 2? P norm minus 2. So the answer, 95%. So this shaded area is going to be 95%. The blue shaded area is going to be 95%. Now let's do it this way, if we can get to exact same number, 95% or not. So it's 1 minus 2 multiply either the CDF of minus 2 or 1 minus CDF of 2. It really doesn't matter. So let's stick with the easier one. So if I just explore, it should be equivalent to 1 minus 2 of those CDF of, oops, this is R, P norm minus 2, I should get the same answer. It's 95.44, right? It really doesn't matter. And for fun, I want you to try this one as well and maybe get that. Barely get that. 1 minus 2 multiply 1 minus P norm of 2. It's the same answer, right? So make sure that you can play. You can go back and forth between these 3 different versions. It's up to you which one you want to pick. You know, usually, but my suggestion is to start by the drawing and then try to figure out which. And again, these are not the only ones that you can come up with. So maybe you can come up with the answer differently. All right, and the last thing is quantile. So we don't get to work with quantile until we get to chapter 3. So this is a midterm 2 onward material, but I'll quickly review it here, but we will get back to it after the first midterm. So if I want to look at the quantile, we use the function Q norm, right? And what is quantile? So guys, look at that here. I gave you this number, the z-score, and I asked you what is the area under the curve. All right, so it was given, so maybe if it is 5, it is 2. This was given, and this was question mark. For quantile, the story is completely the other way around. So you will be given some numbers here. Let's say this is, of course, it should be less than 0.5, right? So let's say it's 0.3. And then you're expected to calculate the quantile. So this is, when it comes to hypothesis testing, we call it critical value. So for instance, if it is 95%, you're here, you're curious to see what is the critical value for one tail. So here's 95. And this is a critical value for one tail test. So if you want to figure out what are these question marks, so we have to use the Q acronym. So Q norm, if it is standard normal distribution, let's see what do we need to pass on. So there are the Q norm, so we need to, if it is a standard, we only need to pass on the quantile. So the quantile is going to be Q. So if I do, for instance, Q norm, this is going to be Q norm 0.3. This is going to be Q norm 0.95. And this is right in the middle is going to be Q norm. Without running this line in R, what is the Q norm of 0.5? What is the z-score? Where are we? Right in the middle. What's the number there? It's 0, right? So you shouldn't be surprised if I run this line, I will get 0. So Q norm of 0.5 is going to be 0. Q norm of 0.95, definitely a number greater than 0. So it's 1.64. Q norm of 0.975, this is 1.95. These numbers, if you have done any kind of hypothesis analysis, this should ring a bell, you know. This is critical values for when the alpha is 5%, for one tail, when the alpha is 5% for two tail, and etc. We get to work with these things, these numbers a lot. Okay, so that's it. Let's call it a day. And when I come to class, I want you guys to review all these things and come to the class with your questions. This chapter, no, this crash course in statistics and probability is not meant to be difficult. So if you see that it is difficult, so it means that you need a little bit more push for your statistics background. So make sure you watch the videos that I shared on Canvas from Khan Academy, or rewatch the video that I did last class multiple times. If you have any questions, please reach out to my emails or myself. And but your job, what I expect you to do is that please, please, please make sure you completely understand the statistics and probabilities that we need for the rest of the semester. Because if you get stuck in this stage, you're going to have hard time understanding the rest of the material for the course. So that's why I emphasize it a lot. So please spend enough time to make sure that you feel comfortable working with the properties and the things that we covered in this crash course. All right, see you in class.